All right, number 30. You guys might be freaking out because this is a modified Haber process for making ammonia is conducted at blah, 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 blah. But they don't give you an equation. You can actually search pretty darn easily for the Haber process. It's a pretty simple equation. It's one of the reasons it's so famous. It's a really effective way to make ammonia, which is an incredibly effective fertilizing agent, right? You got to get nitrogen in the ground. Nitrogen fixing is super, super importante. And we use this for, like I said, fertilizer, but we're actually taking the nitrogen from the atmosphere, which you guys hopefully know from your physical science class that most of our atmosphere is nitrogen. So it's pretty efficient way of making things happen. But this is our equation. Okay, I don't mind giving that to you in case you just weren't super fresh on that. So we have the coefficients of 1, 3, and 2. So we're being told that we have kilograms of nitrogen. Now, we are going to be converting grams into moles. Okay, so I'm just going to go ahead and make sure we all are okay with this being 10,000 grams as well. Okay, and it says that is the limiting reactant. Okay, it says that's the limiting reactant. What that's telling me is that all of the nitrogen is going to react. The hydrogen is in excess. There is plenty of hydrogen, right? The amount of hydrogen present is not going to slow this down. It's all going to be up to how much nitrogen is present, and we know how much nitrogen is present, 10,000 grams. Now, we have some conditions here, and we're being asked for a volume of ammonia. A couple of things I want you to notice. Your temperature, you're given a pressure, you're being asked for a volume. This should be a big red flag that you're probably going to be using the ideal gas law. Now, they don't give you a mole value, a value for number of moles for N, but again, we know that there's 10,000 grams of nitrogen reacting. We can simply convert that into a number. But that would be moles of nitrogen. We're being asked for a volume of ammonia. So what we're going to have to do is use stoichiometry to convert into moles of ammonia produced when 10,000 react. So 10,000 grams of nitrogen. That's N2, by the way. You want to make sure that you remember that's a diatomic molecule, or else that'll really mess up your next step. Because in every 1 mole of N2, there's 28.02 grams, just 14.01. That's 1 nitrogen atom. There are 2 of them here. And for every 1 mole of nitrogen consumed, there are 2 of ammonia produced. Right, again, that's according to my balanced chemical equation. And after this, right, grams of N2 cancel, then moles of N2 cancel, and the only thing I have left is moles of ammonia. I'll have a mole value for ammonia. Later. Where's my calculator? Oh, there's like. I'm all kinds of out of whack. So 10,000 multiplied by 2, then divided by the molar mass of nitrogen. You go with 713, 714, around to 3 sig figs. So I'm going to take this value and I'm going, this is moles of NH3 right here, moles of NH3. I'm going to plug this into the ideal gas law, and we are going to solve it for volume. So it's going to be nRT over, right? So here's my N, here's my R, and that's my T, but I need it to be in kelvins, so I need to add 273 to it. Add 273, it actually ends up being 823. And my pressure and we're ready to calculate. Let's see, just get this over. So times that by R, then by 823, because we have to have that in, and 250 atmospheres. That's a lot. All right, now the data given to me by the question is using 3 significant figures, so I need to use 3 significant figures. So I'm going to have this be 193 liters of NH3. Again, I know you might not be super fresh on what the Haber process is. It's actually used in this textbook, so hopefully we're okay. But either way, I gave it to you, so you can do the stoichiometry.